This is a review of kinetic molecular theory and phase changes. So we have gases, we have liquids, we have solids. So gases, the particles feel very little attraction. There are intermolecular forces, but they're moving so rapidly and they're far enough apart that they're not attracted enough by each other to condense. When the particles slow down, then they can begin to condense and they cling together by intermolecular forces. And then in solids, the particles are held in rigidly ordered arrangements. So we're going to look at how that ties in with a heating curve. So here's a heating curve where we have the temperature, and in this case we're looking at H2O versus the heat added. We are going to start in the solid phase, and we would use Q equals mc delta T there. Then we have the liquid phase where the energy is going into overcoming the intermolecular attractions between the particles. In the area here, the heat is going into making the particles move faster and faster, so we're staying in the liquid phase. Then we have delta H of vaporization, where again energy is going into overcoming intermolecular forces. And finally we have the gas phase. So let's look in a little more detail. So in the solid phase, if we're looking at water, we have intermolecular hydrogen bonding between each and every one of the water molecules. So they're held very rigidly in place. Once we begin to add energy, however, some of the energy or some of the IMFs will be overcome and the water will go into the liquid phase. So if we look at our solid phase here versus our liquid phase, notice that what has happened here is we still have most of the IMFs. So roughly 3/4 of the intermolecular hydrogen bonds remain. They are breaking and reforming at any given time in the liquid phase. Now, as we continue to heat the substance up, we are going to break all of these various intermolecular hydrogen bonds and we'll go completely into the gas phase here. And now all IMFs are overcome. So a discussion question or question you might see on the AP exam would say, why is the molar heat of vaporization for any substance always larger than the heat of fusion? Well, if we look at what's going on during melting, intermolecular forces are breaking and reforming as molecules slide past each other, so only a fraction of the IMFs are overcome. But in vaporization, all of the intermolecular forces between the neighboring molecules have to be overcome for the molecules to separate completely in the gas phase. So here's a graph of water's melting, and we have the actual values here. Notice that it only requires roughly 6 kilojoules per mole to melt a mole of ice, but it requires 40.7 kilojoules per mole to completely vaporize a mole of ice. So the big difference here is during melting, only a fraction of the IMFs are overcome, but during boiling, all of the IMFs are overcome.